In part 2 of the lecture, I will discuss the formation of images by light reflected from curved mirrors. Let's first discuss concave mirrors. First, I want to introduce some terminology that is related to the geometry of a concave mirror in regards to reflections of light. So here is the concave mirror. The back is the non-reflective surface of the mirror, and then the reflective surface of the mirror is on the front here. Now we have this imaginary straight line, which is called the optic axis. And the optic axis bisects the mirror. So splits it into two equal parts. So again, this is an imaginary line. On this imaginary line, we have the focal point F, labeled with capital F. And this is the point where all light that is incident upon the mirror, parallel to the optic axis, is going to be focused. So all the light that is incident upon the mirror, parallel to the optic axis, after reflection will converge at that point, the focal point. The distance from the focal point to the mirror is the focal distance labeled with lowercase f. Then we have point C, also on the optic axis, and this point denotes the center of curvature of the mirror. As you can see, this mirror is a part of a sphere, and so point C is at the center of that sphere. So again, point C is the center of curvature of the mirror. The distance from point C to the mirror is the radius of the mirror. So F is the focal point, this point right here. Lowercase f is the focal distance, that is the distance from the focal point to the mirror. Then C, point C right here, is the center of curvature of the mirror. And R is the distance from the center of curvature of the mirror to the mirror itself. There is a relationship between the focal distance of a concave mirror and the radius of curvature of that mirror, and this relationship is that the focal distance is equal to the radius divided by 2. Here's an actual image of light rays reflected by a concave mirror. As you can see, the light rays are incident parallel to the optic axis. Again, the optic axis is just an imaginary line. After reflection, all the light rays converge at this single point in front of the mirror here. That is the focal point. This image here is represented below as a diagram where all the important points are listed. So we have our imaginary optic axis. The incident light rays are coming from left to right, and they're all parallel to the optic axis. They reflect from the mirror, and all of them converge at one point, and that point is the focal point. And here, for completeness, we also have the center of curvature of the mirror. Now let's see how images are formed by concave mirrors. The image formation for concave mirrors is analyzed by looking at three particular types of light rays from the incident light beam. Here are those three specific light rays that we need to consider. The first light ray is the light ray that passes straight through the center of the curvature of the mirror. Or in other words, this is a light ray that propagates along the radius of the mirror. Well, we know from geometry that the radius of a circle is perpendicular to the circle at any point. So, since the mirror is part of a circle, that means that the radius here is perpendicular to the surface of the mirror, which then means that the incident light ray, ray number 1, is incident upon the mirror at 90 degrees. And so it is going to reflect at 90 degrees as well. Or in other words, it's after reflection, ray number 1 is going to propagate along the same way which it came from. So the ray goes like this, reflects, goes back like that. Ray number 2 is incident upon the mirror, parallel to the optic axis. And after reflection, as I already discussed before, it will pass through the focal point of the mirror. Ray number 3 is incident upon the mirror by passing through the focal point. After reflection, it will be traveling parallel to the optic axis. So, if I place an object in front of the mirror and look at those 3 rays combined, I can get a picture of the formation of the image of this object. Let's look at this example of image formation by a concave mirror. So here is the mirror, and then the object is placed beyond the center of the mirror. So it is more than 2 focal distances away from the mirror. So then, based on the 3 rays that I discussed on the previous slide, I can form the image of that object. So ray number 1 was the ray that passes through the center of the mirror and travels along the radius of the mirror. This ray is going to reflect and go back the way it came from. Ray number 2 is a ray that travels parallel to the optic axis, and then it reflects from the mirror and passes through the focal point. Ray number 3 is the ray that passes through the focal point. It reflects from the mirror and then travels parallel to the optic axis. The 3 rays converge at this point, and so since those 3 rays were the rays reflected by the tip of the object, they converge at the tip of the image. So this is the image. Let's mark that. Object, image. Okay, so then I can use the same 3 rays for any other point on the object, and that is going to build the entire image here. A few observations and some terminology about the image formed by this mirror. So since the image is in front of the mirror, right here, then we say that the image is real. Remember, when the image was formed behind a mirror, we called it virtual. So now the image is formed in front of the mirror, therefore it's a real image. The second point is that the image is inverted. As you can see, the object points up, the image points down. So, if the image points in opposite direction compared to the object, then the image is inverted. Changing the position of the object in front of the mirror will result in also change of the position of the image formed by the mirror. So, for example, I can place my object between the focal point of the mirror and the mirror. And then I can use again my 3 specific light rays to form the image of this object. So light ray number 1 is the one that propagates along the radius of the mirror. So it's going to reflect from the mirror and go back the way it came from, passing through the center of the curvature of the mirror. Ray number 2 is incident upon the mirror parallel to the optic axis. And then after reflection, it's going to pass through the focal point of the mirror. And finally, ray number 3 is traveling along a direction that passes through the focal point of the mirror. And after reflection, it's going to propagate parallel to the optic axis. So as you can see, those three light rays diverge in front of the mirror. So they are not going to form an image in front of the mirror. However, if we continue those light rays behind the mirror, we then get an image of the tip of the object. So again, using those three light rays for any other point, every other point of the object, we can form the image of the entire object here. So now the image is located behind the mirror. That means that the image is virtual. So the image is virtual because it is located behind the mirror where it actually cannot exist. Second, the image is erect because it has the same orientation as the object. In the previous example, the image was directed in opposite direction to the object, and so we said it was inverted. But now, since both the object and the image point in the same direction, the image is erect. We also notice here that the image in this particular example is larger than the object. So the size of the image is larger than the size of the object. In the previous example, it was the opposite. The size of the image was smaller than the size of the object. So that means that a concave mirror has magnification. We're going to talk about the magnification of curved mirrors when I discuss the equation of mirrors. Now let's discuss the image formation by convex mirrors. First, a little bit about the anatomy of a convex mirror. So here is the convex mirror. The back of the mirror is non-reflective. The front of the mirror is reflective. This is the imaginary optic axis. Then the focal point is on the optic axis, and then the center of curvature of the mirror also on the optic axis. The distance from the focal point to the mirror is the focal distance f. And then the distance from the center of curvature of the mirror to the mirror is the radius of the mirror. The relationship between the focal distance and the radius remains the same. The focal distance is equal to the radius divided by 2. So here is a picture of light rays incident parallel to the optic axis upon a convex mirror. And so as you can see, after reflection, the reflected light rays diverge from the optic axis. And this is a schematic representation of that same picture. So the light rays are incident upon the mirror parallel to the optic axis. After reflection, they diverge from the optic axis. However, if we continue the light rays behind the mirror, they will all converge at the focal point. Again, these light rays cannot exist behind the mirror because the mirror isn't transparent for light. But we can imagine that they continue behind the mirror like so they will converge at the focal point of the mirror. Now let's talk about the image creation by convex mirrors. So here we have a convex mirror and an object that's placed on the optic axis in front of the mirror. I'm going to consider again the three rays that I discussed previously, and I will use those to form the image of this object. So ray number 1 is directed along the radius of the mirror. So it's going to hit the mirror here, it's going to reflect and go back the way it came from without changing direction of motion. Ray number 2 is incident upon the mirror parallel to the optic axis, and then after it reflects, it's going to diverge from the optic axis. However, if I continue it behind the mirror, it's going to pass, or it will look as if it's coming from the focal point here. Ray number 3 is incident upon the mirror along the direction that passes through the focal point, but after reflection, it is parallel to the optic axis. If I continue that ray behind the mirror, then it's going to converge with rays, the continuations of rays 1 and 2 at this point. So that's where the tip of the image of this object is located. So again, the rays that are reflected from the object, after reflection from the mirror, diverge from each other, so they will never form an image in front of the mirror. However, if I continue those rays behind the mirror, they will all converge at one point, and that is the point in this particular case where the tip of the image is formed. So then I can apply the same 3 light rays for every point of the object and form the image this way. A few observations about the image. First of all, the image is virtual, and that is because it's formed behind the mirror where it can physically never be. And second, the image is erect because it has the same orientation as the object. One third observation that we make here is that the image is smaller than the object. So convex mirrors also have magnification. So curved mirrors are used in various applications in optics and technology, and therefore the formation of images and knowing where an image will form is actually very important. And of course, it's not a random occurrence. There is a formula that can be used to calculate the position of an object in a mirror based on the focal and the image based on the focal distance of the particular mirror. And so this formula is known as the mirror formula. The mirror formula reads that 1 divided by S plus 1 divided by S prime is equal to 1 divided by F, where S is the distance from the object to the mirror, S prime is the distance from the image to the mirror, and F is the focal distance of the mirror. Now there are certain rules for the focal distance, the distance from the object to the mirror, and also the magnification of the mirror. Let's list those rules, but first let's list the formula for the magnification. So for a curved mirror, the magnification M is equal to minus the ratio of the distance of the image to the mirror divided by the distance of the object to the mirror. Here are the rules for the focal distance of a mirror. The focal distance F is a positive number for a concave mirror and a negative number for a convex mirror, which means that when you're writing this formula for the particular type of mirror, if the focal distance is provided, then you're going to take it with the positive sign and substitute in here if the mirror is concave, or you're going to take it with the negative sign and substitute in here if the mirror is convex. If you're calculating for the focal distance and you get a positive result, then that means that the mirror is concave. If you get a negative result, it means that the mirror is convex. Here are the rules for the distance from the image to the mirror. The distance from image to the mirror is positive if the image is real, which means the image is in front of the mirror. The distance from the image to the mirror is negative if the image is virtual, which means the image is behind the mirror. That means that if you're calculating for the distance from the image to the mirror and you get a positive number, that means that the image will be real. If you get a negative number, the image is virtual. And finally, the rules for the magnification. The magnification M is positive if the image is erect, and the magnification M is negative if the image is inverted, which means that when you're calculating the magnification and you get a positive number, then the image will be erect. If you get a negative number here, then the image is inverted. And with this, I conclude the portion about mirrors. Now let's talk about the speed of light. The speed of light in vacuum is the fastest speed that can be achieved, and nothing can have speed faster than the speed of light. So the speed of light was measured experimentally over time by various physicists. The first attempts were made by Galileo, who had his assistant stay on the top of a mountain peak, a good distance from Galileo, and shine a light from a lantern. Galileo was, however, unsuccessful in determining the speed of light simply because the distance was too short for any measurable by the technology available at the time period of time to pass. So therefore, it was just way too fast for him to measure it. Later, so based on those observations, Galileo thought that the speed of light was basically infinite. A little bit later, the Danish astronomer Ole Rømer made observations of the moons of Jupiter that showed that light had finite speed. And so the speed of light was first measured by the French physicist Hippolyte Fizeau in his famous experiment. The experiment was simply sending light through the teeth of rotating gear, and then this light would get reflected from a mirror that's placed a good distance away from the gear, and it would return. When the gear is rotating at the proper speed, the light that is coming back will pass through the next gap in the gear. So it's going to go towards the mirror through that gap, and it's going to return through the next gap. So knowing the speed of rotation of the gear and the distance traveled by the light beam allowed Fizeau to make the first calculation of the speed of light. And he got the value pretty close to the currently known value for the speed of light. The current known value for the speed of light is 299,792,458 meters per second, or as we use it in this course, 3 times 10 to the 8 meters per second. The letter that we use for the speed of light is c, and this is unique since the speed of light is constant and also unique. With this, I conclude the lecture on light.